Hello and welcome everybody to the lecture about protection in electrical power systems. This time I would like to talk about overcurrent protection. This lecture is devoted to the overcurrent protection basis, and I would like to start with a classification of the overcurrent events. Overcurrent events start out of the regular state of the network. So the regular state is the status of normal operation, which is characterized by three features. Feature number one is that the insulation is everywhere intact and okay. That means in all phases and at all locations. The second feature of a normal operation network is that all switches, that means the circuit breakers and insulators, are in their wanted and regular position. And the last one is that voltages and currents are within their nominal voltage range or below the nominal current of a transportation mean of electricity. So when these current-wise conditions are violated, then we speak either of overload or of the loss, in case of loss of insulation, about short circuits. Let's start with the overload. Overload means that the current goes slightly above the nominal current level and then is reduced, whereas in the loss of insulation we have either a single phase to ground fault or a multiple phase to ground fault, which are also called short circuits. The classic classification of these is, as we can see, to my right side. So let's start with the fault class A, which is the three-phase short circuit. This is the most easiest one to calculate, but in reality it is very rare. Three-phase short circuits normally occur only either by closing on ground, that is a switching error, or at the last stage of a developing fault. A developing fault is meant it starts as a single or double phase fault and the arc burns until the whole thing ends up as a three-phase fault. The next one, the double phase fault without ground, is quite rare. It only occurs in overhead lines where two-phase conductors may touch each other while they swing in the air. More common is fault type C, which is the double phase short circuit with ground. This is a phase which regularly starts with a single phase to ground fault, which by the effect of the burning art afflicts the next phases, so that the next phase is also involved and that we have a double phase to ground fault. The single phase to ground fault, as I mentioned before, is the most common one because this is caused by the breakdown of insulation. Breakdown of insulation means we have a field between the hot conductor and the cold ground. And if this insulation does not sustain this field anymore, then we have an insulation breakdown, and this is a fault between phase and ground. The last fault, which is classified here as E, is the so-called cross-country fault. This is a double ground fault in two different phases. This situation occurs in many cases in the aftermath of a single phase to ground fault, where due to the increase of the voltages in the healthy phases, in one of these healthy phases we have another voltage breakdown and we have a second fault point in the grid at some other place and at the second phase. So this is called the cross-country fault. In overcurrent protection I would like to deal now with the typical short circuits, that is phase to phase, between three phases and so on. So, first we look at the current versus time dynamics. Let's start with our standard grid which was already introduced. This is a radial grid. We have in this radial grid from left to right, we have a grid, a transformer, we have a bus bar, we have a metering device given in green, and we have the line with the consumer where this fault will occur. Now let's see in terms of voltages and current what happens at this moment. First we start again with the normal operation. Everything is in the so-called green range. The voltages are more or less okay and the current is below its nominal value. If the current of this means of electricity transport goes above the nominal value, which is given by the dotted line, then we speak about overload, and at a certain time it will go back to normal operation. And now this short circuit occurs. What does it mean? The voltage breaks down and the current goes up to values of some typical kiloamps, for example, 5 kiloamps. The current goes on and on until the protection comes in. The protection has two setting values which are relevant at this point. The first is the pickup value, which is of course below the 5 kiloamps, so that the protection sees there is a short circuit. And the second one is a time delay. The time delay, for example, is given here as 0.4 seconds, and when this time has elapsed, then the protection device will trip the circuit breaker. The current will go down to zero, since the circuit breaker has opened the faulty feeder, and the voltage on the faulty line, of course, goes down to zero. And the voltage in the healthy network, in the other feeders, has recovered since there is no fault anymore in the grid, and the current in these healthy networks feeders, by the way, is more or less the same as before. So this was the voltage and current dynamics versus time. Now let's see, what does protection function do in this situation? So again, we start again with the same basic setting. So that means before something happens, the current is on this feeder is some 300 amps, and the voltage is nominal voltage. When the fault occurs, suddenly a big current comes from the source to the fault. We have these typical 5 kiloamps. The voltage breaks down and the time starts to run until the time has elapsed. For example, at this point of 0.4 seconds. And this means that at that very moment, the protection operates the circuit breaker trips the current path, and the feeder has been tripped out. So at this point, the feeder has no current, it is switched off, and the remaining network is healthy again, and the voltage has recovered again. Look at the picture to my right side. We see that the voltage is again in the green range. So, this was the lecture about the basics in overcurrent protection. Thank you very much.